Hello, this is Dr. Gundikonda Reddy. I would like to explain one of the innovative experiments by our students. Uh, it is about torsion test. We know torsion test for the material for the given shaft we have to conduct on torsion testing machine. But here we did it the same experiment to find out the material modulus of rigidity. We did on UTM, universal testing machine. Actually, instead of torsion testing machine, we are using UTM. That is the innovation here. So we know in torsion testing machine the formula about that formula is equivalent to T by J is equivalent to G theta by L is equivalent to Q by R, where T is the torque that we know in Newton mm. I am writing here Newton meter. It is Newton mm only. I will change it. Newton mm. Newton mm. Then we are having J, polar moment of inertia, mm to the power of 4, and modulus of rigidity G, it is Newton for mm square. This actually we would like to find G value. Its value varies from 0.6 to 0.9 into 10 to the power of 5 Newton for mm square, that we have to get it. Then the theta is angle of twist. So this is degrees we are getting, that we can convert into radians. How we can convert degrees into radians? It is 1 degree is equivalent to pi by 180. So we can get in radians. The conversion from degrees to radians is 1 degree is equivalent to pi by 180 radians. Likewise, length of the shaft is in mm. I can write in mm. Right? Then shear stress. The shear stress is Newton for mm square. Likewise, radius of this shaft is mm. Just see, it is in mm. So here just see in the formula, here our aim is to find out the modulus of rigidity G. So I am taking the formula, this part of the formula only. I am not considering this part. It is need not required at this moment. So if you are knowing the torque in torsion testing machine, J is polar moment of inertia. Its value is pi d to the power of 4 by 32. These two things we are getting from the machine. G value we have to get it. Theta value we are getting directly from the machine when the twist is taking place, the shaft twist. L length of the shaft is given and we can measure it. That is actually how we did it on torsion testing machine. But we are not having a torque on UTM. That how we are going to do it. I will show you in the lab what we did it. You just see the UTM, just see this upper gripper, bottom gripper and the base, and is operated by this entire system, hydraulic system like this. The pipes you can see it. So here we are applying the force. That one, we prepared one kind of equipment innovatively. I would like to do torsion test on this machine. This is what we did it. This horizontal we are having the steel frame, steel plate. We are fixed steel plate. It is we are taking depending upon random value of load. We are taking some 10 to 15 mm thickness sheet. You just see that. And we are having two vertical rods. They were welded to the bottom sheet. And for support, we are providing the bracket here, and we are having one more bracket here, the other bracket this side, and here also we are having one more bracket. And because to have the support, otherwise it may fail during its operation. Now, here the shaft where we would like to find modulus of rigidity. See, the shaft is fixed here. Here we are having the groove, circular groove. Just see it, circular groove. Shaft, this is the shaft. Other side, it is a circular groove, no? It is rotated. It is to be rotated by from this side. So here, other side of the shaft is not circular one. Just see it. It is, you just see all of you. It is some kind of rectangular shape that is provided. That is the square groove at the end made of rectangular part. This is grooved here and now. So what happens is, this is a steel rod. It is a pin kind of thing that is observing here. This we are keeping at this place. We are applying the load at the top. We are keeping this entire thing after keeping the shaft into these grooves. This entire system we are keeping under the anvil of this UTM. We are trying to apply the load from this top point, this point, from this point, finger where I am showing. As we are applying the load is recorded, how much load we are applying. For that load, you just observe it, this entire system is trying to, it is there like this. It is trying to rotate this entire thing. When it is trying to rotate entire thing from horizontal, the vertical distance can be calculated by using the dial gauge. At this point, we are providing the dial gauge with my finger place. So, what is the vertical distance it is moved? That we can calculate. If you are knowing this vertical distance, how much is traveling, and also we are knowing what is the distance of this point from this place. So, this distance we know it, and this distance we know it, and this angle we can find out now. I will tell you separately that angle we can find. Now, you just see in the formula, the load we are taking from here at the top, the load we are taking from the top in UTM. To have the torque, we have to have force into distance. What is the force here? This is the force which is recorded in UTM, and the distance is from this point to this distance. This is what is torque, force into this distance. We are getting the torque. J is polar moment of inertia. So, what is the polar moment of inertia? J is equivalent to pi d to the power of 4 by 32. D is the diameter of the shaft. This diameter we can find. So, even we are knowing J also. T by J. Then is equivalent to, in the formula, G we have to find out. That is required to find. And theta as I am showing we are getting from here through the dial gauge by L. L is length of the shaft. From this point to this point we have to take it. From this point to this point we have to take it. Here everything we know it except the G value. So when you are providing all these values for a particular value, for a particular rotation, particular movement of this dial gauge, as it is rotating downside, the force we can calculate. What is the rotation, vertical distance it is traveling, we are knowing it. When we are knowing this vertical distance, we are knowing the value of theta. Once we are knowing the theta, we can find out torque, force into distance. So now we are substituting here. I will show you once again here. It is torque is force into distance. It is force into torque is force into distance. I cannot write R since that R is different. It is the distance, force into distance. So then J value is 5 to the power of 4 by 32. Here G value we would like to find out. The theta we have to find is, how we can have it? It is the shaft that is trying to move it. So from this point it is moving now. So here we are finding with the dial gauge like this. Let us say we are having the rotation of like this. This is what is theta is. So if you are knowing this theta, So how we can get it? We can find out this angle. Let us say it is R. It is R. This R is different. This R, otherwise you can take some S. So how we can find L? For smaller angles, L is equivalent to this formula we can apply here. You just see, here we are having, we know, we would like to find theta. We know these distances. Let us say it is L. The theta, how we can find the theta? So the formula is L is equivalent to S into theta, like that. So here we know the L value, here we know S value, we can find theta. So in the formula, if you are substituting all the values, we will get G value. The G value we know it varies from 0.6 to 0.9 into 10 to the power of 5 Newton per mm square. That is how we have to do it. So this project is did by some time ago, our students. So they are well placed, they are working in good companies. We feel it is a good project did by our students some time ago. Thank you.